So, hello everybody. My name is Jan Spacek, but feel free to pronounce it Jan Spacek or Jan Space K, which is even better. I will be talking about actually looking for life on Mars with heavy lift, which is the topic of this conference. And I will be talking about how we are trying to find life on Mars before humans arrive on Mars. We started an organization called ALFA Mars, and I'll be talking about that. So in my talk, you will find out how to find life based on unknown biochemistry. How do you find life with unknown ecology? And how do you do it when you have maybe 4, maybe 6 years to do it, very short periods? So ALFA Mars stands for Agnostic Life Finding Association Mars. For now, you can just say that it's alien life finding. You will understand later why it is agnostic. So our team, this is me. I'm a molecular biologist and electrochemist. Stephen Benner is the main finance supporter right now. He was speaking this morning, so he already introduced himself. He's I would say, a science generalist, specialist in chemistry, but made breakthrough discoveries in molecular biology as well. Victor Parro and Lyle White are world-class astrobiologists. Both are microbiologists specializing in extremophiles. Victor Parro is a director of Spanish Centro de Astrobiológica, and Lyle White is from McGill University. Shannon Butcher and Olivia Trankley, they are helping me right now to design the instrument. So I work in Florida, but for this project, I moved over to Eugene, Oregon. And I would mention one more person, Janusz Petkowski, which is Deputy Director of Venus Cloud Life mission, a mission which is sending, that's the first interplanetary mission. So he's helping with this project as well. The rest are students, postdocs who are helping us. We have Chris Tanby over here. So yeah, we are still growing organization. So if you want to join, you can join us as well. So what was the motivation to start ALFA Mars? Well, to me, the more I know and the more we know about life on Earth and extremophiles, the more we are certain that there very likely is life on Mars. And surprisingly, although we are quite sure there is life on Mars, we have not sent missions to look for life on Mars since the Viking era. So this was the last mission. If sent to Earth poles or if sent to Atacama Desert, would be able to find life on Earth. So none of these missions, not even planned missions in the future, would be able to find life. And NASA astrobiology currently predicts that we will return to looking for life on Mars in 2042 or in 40s, which means that we will likely have humans on Mars before we had a chance to look for life on Mars. Like all these missions, which say they are looking for life on Mars, they are looking for signs of past life, or they are looking for biosignatures. So yeah, NASA is not interested in looking for life on Mars. So in the morning, we had a presentation how we will return samples from Mars. I made this joke in April 1st last year, and it's turning to be less of a joke, as we are predicting to send humans to Mars long before we'll be able to return the samples from Mars. I'm looking if we have some people who understand Chinese in the audience, but yeah, never mind. So it seems that NASA astrobiology does not believe that anyone on Earth will be able to get to Mars before like 2050s. On one hand, everything we send to Mars or trying to bring from Mars has to be meticulously sterilized. And on the other hand, NASA does not plan to look for life on Mars before 2040s. So, and NASA itself plans to send humans to Mars, and know that humans cannot be autoclaved. So we have this discrepancy that up until year 2040, they are trying to not bring any bacteria to Mars or bring any bacteria back. But suddenly in 2040, we decide, oh, screw that. We didn't need to do that. So my personal analysis about sending humans to Mars before we know if Mars has active biosphere, while I believe it can be easily achievable. On one hand, it increases the sense of adventure. Don't get me wrong, I'm an adventurous guy. So I can understand why NASA is choosing this point of view. On the other hand, it's not very smart. I had it written in different words before, but I adjusted it a little bit. So why we don't want to work with NASA, why the ALFA Mars is private organization at this point. Stephen already mentioned the consensus approach in astrobiology before, so I'll just say that I find it very strange that National Academy of Sciences needs to tell NASA that the scientific process of multiple working hypotheses is the most rigorous and time-proven means by which to assess evidence and claims related to life detection. One would assume that NASA already knows that, but apparently they have to be reminded. Well, and perhaps over time, NASA will realize that it's a good idea to look for life on Mars before we have humans there. But as you know, there's not much time to wait. In standard NASA missions, it takes like 20 years from the conception of mission to execution. And right now we have maybe 6 years before, maybe 8 years before we have humans on Mars. So that's why we decided to start the organization ALFA Mars right now. Now for the positive motivation, the inspiration, that's the mission. I'm proud to announce that I'm a member of the team who is sending the Rocket Lab rocket to sample Venus atmosphere, not sample, to analyze Venus atmosphere using autofluorescent nephelometer, which is an instrument that shoots laser out of a little window and analyzes reflected or light or fluorescent light. And the laser wavelength was tuned based on experiments I've done with my student in Stephen Benner's lab last summer. So this mission will be verifying my hypothesis about organic carbon cycle in the Venus atmosphere. So because this is not Venus Society meeting, this is Mars Society meeting, I'll have just one slide about it, but I would be happy to talk about this with you if you ask me later on. Just one thing, this was important for me because I realized that not only NASA is able to do interplanetary missions, so we can do those privately. So we don't want to prevent anybody from going to Mars. If you can do it, go for it. But ALFA Mars want to make sure that by the time we are able to go, we know if there's biosphere on Mars. And of course, the instrument which I'm going to introduce a little bit later on, can be used when we have humans on Mars as well. So let's not postpone human missions to Mars after. We have astrobiological survey of Mars. We have to do it before we get there. So finally, to the scientific questions. How does ALFA Mars remain agnostic to our biochemistry? How do you find life that we don't know what is based on? So quiz for everybody in audience. How many of these do you think are made by life? And again, it's a trick question. None of them is. They are all false positive biosignatures. And many biosignatures are like these. That's why NASA astrobiology proposed that consensus science, that when we see some biosignature, we need multiple biosignatures from the same location to signify that it actually comes from life and is not produced biotically. But in some cases, it's clear with just single observation whether we detected life or not. And genetic polymers or polyelectrolytes are one of those examples. So genetic polymers cannot be produced abiotically. They must be produced by life. Well, they are actually required for life. And instead of looking for molecules that are produced, that might be produced by life, we are looking for molecules that are necessary for life existence. Without genetic polymers, you cannot have evolution, and without Darwinian evolution, you cannot have life in any form, including alien mind. So looking for genetic polymers, avoid false positive, such as methane or morphology I showed you on previous slide. It avoids false negative results. If you look for cellulose or some molecule which is common in Earth life and don't see it on Mars, it just might mean that Martians have not invented this kind of biochemistry. And genetic polymers must be either polyanions, like DNA in life as we know it, or it can be polycations. Together they are polyelectrolytes, negative or positive charge in the backbone, and they have to have some information units which are similar shape and size. So that's why Alpha Mars approach is agnostic towards searching for life. As long as you find genetic polymer, you know that you found life. So how do we remain agnostic towards ecology? After all, we don't know what Martians prefer. There are many opposing ideas where we should send rovers to find life, if permitted by NASA, of course. We step aside this issue by sampling entire planet, and I'll explain how we do that. But for that, you need to understand how Martian climate changes over time. So right now, we are in a situation where Mars have a quite small obliquity. That's the tilt of the rotation axis, but it can get very low to very high obliquity. During that high obliquity, the ice and precipitated carbon dioxide sublimates, and then snow in mid latitudes. And then over summer, it's retained. So in high obliquity periods, you get Mars, which has a much thinner but larger in area polar caps. And those glaciers are staying in mid-latitudes up to this day. So during that period like now, we have small thick polar caps, low humidity, cold summers, and low atmospheric pressure. And the high obliquity period, it's in the reverse. And if such life, well, if such ice was on Earth, it would definitely contain life. So we can see the ice deposited from the last warm and moist period in these radar observations, and we can actually see when we have impacts, we can see the excavation of the ice laying very shallowly. Notice this is between 10 centimeters to less than 1 meter. So here's my lasagna ice hypothesis about how life is deposited in this mid-latitude ice, which we can see in this cliff. Or, well, and now Martian life is basically waiting for the next warm period in the lasagna from which we can sample it. So, as I noted before, if you just sample one side, you can miss the life. That's why we decided to look for life in the lasagna ice, where it's deposited from the entire surface of the planet. Now we need to pre-concentrate because the life is going to be very much diluted, very likely, And also Mars is not very energy. There is not much energy for bacteria to use, so we expect life to be sparse. So we will need to sample very large samples. Because if you sample just 1 milliliter and life exists in like 10 bacteria per 1 liter, you might just miss the right milliliter. So the idea is, instead of sampling 1 milliliter, let's just sample 100 cubic meters. So the problem is solved by somebody giving us a sample of 100 cubic meters of Martian ice, and we can find life on Mars. But who should do it? And the answer is SpaceX or any other agency which is following Mars Direct architecture. Here I don't need to introduce Mars Direct, which is making propellant from local resources. But any ISRU can be used if whoever first mines ice on Mars can be the first to find life on Mars. So that's the goal of our mission. How the mining is going to be done? Very likely using these rod wells, where you make a hole, pump hot water in, melt some Martian ice, and pump it back, repeat. And ALFA, the detection instrument, would be sitting on this pipe, analyzing the water before it is used. So notice that we are not proposing a separate mission, we are proposing add-on to existing missions. So if somebody plans to go to Mars, we can provide them with a means how to find life on Mars. So because first, before you go to Mars, you need to send those robotic missions. We are sure to have somebody sending those missions for us before sending the humans. Right. It's quite small instrument, consuming very small amount of energy compared to how much energy will be needed for refueling a rocket. And so finally, I'm getting to the technical side of the thing. Alpha Mars is ALFA, which is the concentrator, and analyzers. So analyzers are already established. I'm not going to much detail because I'm running out of time. It will be mass spec, min ion, and other techniques which are already established on Earth. More about our approach that's based on using electrodialysis. If any one of you had a low sodium soy sauce, it was using the same method we are going to be using to extract genetic polymers on Mars. It's basically based on a quite simple approach. You have those greens are membranes with different size pores. So you pump in the middle stream feed of molecules. Negatively charged molecules are pulled towards anode, positively charged are pulled towards cathode, and then you separate them by size. So on Mars, we are going to do the same thing. Instead of soy sauce, we are going to be pumping ISRU water in and isolating, purifying, and desalting polyelectrolytes, polyanions, and polycations, which can be concentrated from a huge amount of Martian ice. So now I'm working with this team in Oregon. These people were helping me while I was in Florida. Instrument at this point looks like this. And on Monday, I managed to separate sulfate from sodium, making sulfuric acid and sodium hydroxide streams. I bet that next week I'll be able to separate food colorings which are charged, and weeks after that I plan to do some work with actual DNA. So milestones before end of this year, I hope to have a working prototype in my hand. Then we will combine it with methods which already exist, and people are already waiting with the analyzers for our steps. Then those astrobiologists I mentioned in the beginning, they have access to Antarctic and high Arctic, so they will help us with establishing missions there to look for life. And then we will make automatization and miniaturization, work on space readiness, and we should be ready to send the thing to Mars by year 26. Well, we'll need help from you to achieve this. You can go to alphamars.org, and you can. We will need some financing. We can join the project. You can help with the work, publicity, and if you have contacts to people who are going to mine ice on Mars, that would be very helpful. So, in summary, I am not going to do summary because I'm already over time. This site should be on very soon. Thank you for your attention. And
thank you very much. Do we have any questions?
I'm wondering how agnostic your search for life is in what possibilities, if any, of you have excluded. So, for example, the theoretical possibility of silicon-based life as opposed to carbon-based life. Where do you draw the lines in terms of what you plan to look for?
So, yeah, if life, so if that depends how you define life. If you believe that life is evolving, was not created, then it has to have some molecule which is replicated and which can mutate, and for that you need polymer, which is charged with either polycation or polyanion. Stephen was talking about that in the morning, but I hope that this answers your question. I don't think that there will be silicon-based life anywhere, because silicon is not very good for complex chemistry. So, but still, if there's silicon-based life, it would still have some backbone, some molecule which can be detected.
Can you clarify, is the goal to detect genetic polymers free in the environment as remnants of dead life, or is the idea to separate out the genetic polymers from extant life?
Yeah, I didn't have enough time to say that we are going to be sonicating the stream, and also DNA does not survive for more than about several million years when it's alone in the ice. So if we find DNA, for example, then it's quite likely that it's from recent past. It cannot be like a billion years ago, because by that time it would be totally decomposed.
Is that the case of all genetic polymers or just DNA?
Well, we know about DNA. Of course, I cannot give you a serious answer about polymers. I don't know, but yeah, some samples will be sent back as well. So, yeah.
Thank you so much, Jan. Thank you so much.